So last Tuesday, we have defined a real value function on f, okay, by this formula. Okay. All right. So, so any questions about the material we covered up to now? Okay, so if no questions, then I will proceed to complete the proof. Right, now for any atomic event in C, we know Cg is just equal to G itself, right? So, because G itself is an atomic event. Okay. So that when we evaluate these functions, then by definition, prong, okay. So this is just equal to but thinks this collection consists of only one member, which is G itself. So this is actually G. Okay. So the newly defined function f have the same value as the p functions, because originally p function is a function defined on the collection of all atomic events only. Okay. Okay. So that's fx an extension of f of p from C to F. Okay. All right, and so now we will show that the function f is a probability function. So first of all, it is clear that f is non-negative valued. Okay. Because the sum of because p function is non-negative value, so every p of g is non-negative value, and you take the sum, is still non-negative value. Okay, and by exercise, right? So I mentioned an exercise last Tuesday that the total event is the joint union of all the atomic events. Okay, in the collection of all atomic events. So the total event is just the union of all atomic events in F. Okay. And then the f of x, so f of g in OC. And we know this is equal to G or C PG. Okay. But we know P satisfies this identity. So the summation of PG over for G over all C is equal to 1. So this is 1. Okay. So the function value of the total event is equal to 1. Okay. So that's F satisfies axioms 1 and 2 of a probability function. Okay. Right, now we have to show that F satisfies axiom number 3. So we consider a sequence of mutually exclusive events E1, E2, etc. in F. Okay. So the situation is here. So this is our sample space, and we have disjoint. This is E1, this is E2, etc. Right? And these events are mutually disjoint. And we know every event is a disjoint union of atomic events in the event. So the partition is here. So it's quite here. So this is G. Suppose G11, G12, G13, G14, right? And here, E sub 2 is the disjoint union of all atomic events contained in E2. Suppose that, etc. Probably only 3 components, etc. So from that, so it can be seen that the collection of all atomic events contained in the disjoint union, okay, is equal to the disjoint union of C sub EI. Okay. Any questions about this identity? Okay. Right. So the union of E sub I, okay, contains atomic event like G11, G12, G13, G14, and G21, G22, and G23, right? So you just take the unions and all this. So you can see that G1 are mutually exclusive, and we have this identity. Okay.
G is the atomic event. G is the atomic event.
Yeah, they are all atomic events.
What is C?
C? See here? Inside E, there are a lot of atomic events, right? Yeah, so we collect all the atomic events inside E. Collect them.
So the collection of all the atomic events is.
So, well, and then when you take the union, that is become to E, right? Because atomic event is building blocks. We prove in a proposition 2.5.d, right? In the fourth proposition, that every atomic event, every event like here, is built by atomic events, right? Mm-hmm. And so for this specific case, the CE1, just G11, G12, G13, and G14.
So
Okay.
C1 equals E1
Yeah, C sub E1.
equals E1.
No, this is collection of all atomic events inside E1. Okay, and for C sub E2, because inside E2 there are 3 atomic events, so we just write down, etc. Okay, okay. Okay, and so because EIs, they are mutually exclusive, right? And so that atomic events, okay, contain in individual event E sub I, they will be different from each other. Okay. Okay, just like so C sub E1, C sub E2, they are mutually exclusive, and if we take the union of the events, then the corresponding collection C would be the disjoint union of the collection of each sub E sub I.
What does this symbol on the left means?
In here,
Yeah,
the index, just union of E sub I.
so collection of all the.
Yeah, all the E, yeah. You may, okay. If you define E to be, okay. So, okay. This is a more directed way to write down the relationship, but you can use E as intermediate symbol to denote the disjoint union of EI. Mm-hmm. Okay.
It's clear now.
Yeah, great. Because this is very important. If you can understand that, then you will understand the following statement. So, good for you? Good. All right, and so the function of okay, right. So so what is the function value, f value of this union? Now we know by definition, this is just the f of disjoint union, and the G belongs to E, and okay. Okay, maybe maybe I will say the union. Okay, so this is, we know this is just okay. if you use CE, maybe you can it's more direct way, but if you're not, you can say, all right, f of e. So we define this one, right? F of e is equal to okay, it's good. So maybe I erase that. Okay, so that maybe I use this. Right, and so by our construction, by the definition of G, so this is equal here. This is the summation. G is in CE and P of G. Okay? And because C sub E is equal to the union, right? So this is summation. G is in the union. I from 1 to infinity. CEI and PG. Okay. Yeah.
What is f of e here? How can we define it?
F of E? Yeah, because we define a new function. F of E by this definition. Yeah. Last Tuesday we defined a new function, right? Yeah. And the new function is defined in terms of P of G. Because P only defined on C, right? On atomic events. Originally, right? The P has value only on atomic events. Okay. But we want to extend P to a function. We say F, and this F can take values on every event in the sigma algebra. Okay. Because as we know, even though the F can be uncountable, but the collection of C is countable. Right? Yeah. Yeah. So this is a big extension. Big extension there. Okay. But this definition is uniquely defined because, as we know, that every event E is just the union of all the atomic events inside the E. Okay. So our purpose is to show F, this F function is a probability function. Okay. And to show a function, a real value function on the sigma algebra F is a probability function is to satisfy 3 axioms. Right? We enumerated before. And axiom number 1, number 2 are quite obvious. Okay, for axiom number 1, because by definition is non-negative valued. And for normalization, axiom number 2, we have to show f of x is equal to 1. Okay, and the exercise I raised up last Tuesday to show a total event is actually the union of all atomic events in F in the sigma algebra. Okay, so the G is run out of all the members in the whole collection C. Okay, and so with that, by this definition, this is a summation of PG, and the G is over all members in C, and we know that it is required, right, is equal to 1. Okay, so we have the non-negativity, we have normalization already. So the only axiom left to prove is to show that F satisfies axiom number 3, means countable activity. So we consider a sequence of mutually exclusive events. Okay. Okay, and we let E to be the union, the disjoint union of EI. Yeah. Okay. And we know the subcollection C corresponding to E is just the disjoint union of the subcollection C and sub E sub I. Okay, now, and because that the collection, they are disjoint union, so the summation is actually the double sum PG. Yeah. Okay. We can split the sum into double sum. And summation I from 1 to infinity. But by definition, what is this? This is probably this is just f of EI. Okay. Okay. So our conclusion is that f of union, okay, which is f of E, which is okay. So f satisfies axiom number 3 of a probability function. Okay, so we proved there exists a probability function which is an extension, okay, of P. Okay. So we proved the existence of a probability function. Now we show the uniqueness. Assume that there is a probability function G on F which extend P. Okay. Okay, so suppose we have arbitrary, just a probability function G, okay, and which extend P, i.e. G of G equal to P of G for all atomic event in C, okay? Okay, now for any E in F. Now consider an arbitrary event E in the sigma algebra. Okay. So G of E, okay, is equal to G of okay. And this is equal to summation G. Why? So this is 1. C of E is countable. Okay. By proposition 2.5 on D. Okay. Second, okay, G satisfies because G is a probability function, so axiom number 3, counted by additivity. Of G. Because G is a probability function, so it has counted by activity. Alright, so if here, this is the disjoint union of countably many events, right? So that this is equal to the summation of the PG. Okay, so this is by countable activity. But this is exactly a EFB by definition there. Okay. Alright, so for any event in F, G and F has the same value. Thus, G is identical to F on the sigma algebra. Okay. So thus, the extension of P from C to so the conclusion is that thus there is one and only one extension of P on C to a probability function on F. Okay, so this is complete proof. Any questions about the proof up to now? Okay, so proposition 2.5.E would be quite useful, right? To define a probability function, it is sufficient to define a non-negative value function on the collection of all atomic events, such that the summation of the probability assigned to atomic events equal to 1.
These atomic events are included in all the events, right? E1, E2, E3.
Atomic events are these events, okay? So they are. So we just assign probabilities to atomic events, such that the sum together equal to 1. Together.
Atomic events of all the events E1, E2, E3 combined will give 1.
Well, not okay. Here, right? To prove the countable activity, we just assume E1, E2 they are disjoint from each other, Okay. Okay. But it's possible. It's quite possible because we show in exercise. We show that the total event, right, is actually equal to the union of all atomic events in the sigma algebra F. Okay. So of course, if you look at the S, then you of course you will see that they comprise of atomic event like that. They are all atomic events, that's true. So the whole X will compose of atomic events. Okay, and their union, the union of this atomic event becomes to S. Yeah. Okay. But all these results has a pre-assumption. I have shown that every event in F contains an atomic event. Okay? And I have demonstrated that if the sum space is finite, okay, then every sigma algebra will have this property. But if the sum space is just discrete, means that it is possible, it is infinitely, it is countably infinite state. Okay, so even though the S is still discrete, but it has infinitely many outcomes. But if you select the power set of X to be the sigma algebra, okay, then this is also true. Okay. And so in practical situation that they all satisfy these requirements. Okay, so example. Okay. For finite sample space X with equally probable outcomes, and F equal to X. The assignment okay, so the assignment uniquely specify a probability function on F, and P of E equal to okay. Right, so even though we assign the probability to each singleton, because in this case, atomic events are just singletons, okay? And so we assign equal probability to each singleton, okay? To predict one. And you can check that summation. All right, so we know, okay. So here, okay. So the collection of all atomic events is just the collection of all singletons. All right, and the summation okay. So this assignment on the atomic events satisfy the requirements in here. Okay. In here. Huh? Yeah. And so that this assignment gives us a unique probability function. Okay, by proposition 2.5.e. Okay. Example. So let x equal to and okay. So suppose that x is a countably infinite set, omega 1, omega 2, etc. So there are infinitely many outcomes. Okay, and the sigma algebra selected is just this power set. Then again, C it's equal to so that is omega 1, omega 2, etc. Okay, so atomic events are just singletons. Okay, and so to assign a probability for so we let P1, P2, okay, be a sequence of non-negative numbers with the summation Pi equal to 1. Okay. Yes?
This is statement that let P1 and P2 be a sequence of non-negative.
Oh, yeah, sorry, thank you.
I think that this could also be written as like P1, P2, like the index should be belonging to positive real numbers, positive integers.
Not necessarily P1, P2, because if they are integers, this is possible, right? Because you have to sum to 1. For example, you may relate this equal to the summation. Okay, this is series converge, right? and we say the sum is delta. Okay, and we define P sub I to be 1 over delta times over I square. Okay. Okay, and then you sum over P sub I. So this is one. Okay. Right, so this is just one of possible non-negative sequence. Okay? So that their sum is equal to 1. Okay. Actually, you have a lot of. This is always true if there's our power, if r is greater than 1, right? So this sequence converge. Okay, if alpha, for all alpha greater than 1, okay, you can define delta alpha here, and you can define still get 1, right? Okay. So you have infinitely many such sequences of non-negative numbers. Right? And now define. So the assignment. So the probability okay. All right, so for the singleton consistent of the first sample, the ith sample, the probability assigned to be pi. Okay. So if you do this probability assignment, all right, so that give us a unique probability function. Actually, maybe I will say uniquely specify a probability function. On the sigma algebra. Okay. Okay, so this kind of assignment is quite common. Okay, very common. So this job of probability assignment to atomic events is not formidable, right? It's still controllable. Okay, but if you want to assign probability to each event in this set, it becomes terrible. Because why? Because this collection of events is uncountable. In this case, because this policy is uncountable. Okay, any questions? Any questions? So okay. Right. So the last section is about very spatial probability, about the probability function, the continuity of the probability function. Okay. We know probability function is a function defined on the sigma algebra, right? Because the members of the sigma algebra are just subset of the sample space. Yeah, sample space there. So we call it's just so-called set function because it is a function defined on collection of sets. Okay. All right, and we have to address the continuity, right? What do we mean the continuity? So let's E1, E2, En plus 1, okay, be an increasing sequence of events in F. Okay, so it's become bigger and bigger. Okay, and we define the limit of this increasing sequence of events as here. Okay, because it's become bigger and bigger, so we want to know, we define its limit, and this limit is just the union. Okay, of E sub n. Okay, so we just defined it. Okay. So which will be denoted as En go up and the limit x. Okay. Right. So for an increasing sequence of events, we define this limit as the union. All right. And another situation may occur that if we have a decreasing sequence instead of increasing sequence of events. So let's E1 contain E2, contain En, and the En plus 1. Okay. So B, a decreasing sequence of events in F. Yes?
For the first one, E1 is a subset of E2. Does that symbol means that it could also be equal to E2?
Yeah, it is possible equal, yeah.
Would that still be called increasing sequence?
Yes, just like 1, 1, 1, 1. It's increasing sequence.
That's an increasing sequence?
Yeah, because in the definition, inequalities, for example, we have this one, right? Okay, but you will say that this is so-called strict inequality, right? strict. Okay, we use the, so that if E1 but not equal to E2, which means that the E1 is the, improper, is a proper subset. Okay. Yep. So it is possible, yes, E1 may be equal to E2, so it's still called increasing. Yeah. If we say strictly increasing, then we should say that you can't have equality. That is a strict increasing. Yeah. Okay. Okay, so for a decreasing sequence of events, when we define the limit of this decreasing sequence of events as here, the limit n goes to infinity En is defined to be the intersection. Okay. And denoted as going down, right? Decreasing to the, and the limit is just there, intersections. So there are two situations that we can define limit of sequence of events. One is if the sequence of event is an increasing sequence of events, so this become bigger and bigger, so the limit will be their union. The other situation is we have a decreasing sequence of events, so the limit is just their intersection. Yeah. Okay, so the limit, this concept only apply to these two situations. So
what does it mean when you say the limit of an event? What do you mean?
The limit.
The limit of an event. So
yeah, the limit of an event. We have sequence events, and so we want to know, because, for example, we have a question that whether if it becomes smaller and smaller, right? So what is the so-called asymptotic, or we call limit, right? Of the
event is set of some possible events from the sample space. Let's say E4 or E5.
yes.
So when we say the limit of the event, do we mean that the number of elements does it have?
It is possible the limit of the event, which means that by our definition is the intersection, right? So this could be a null event or not a null event. It depends. Okay, it depends. Okay, so in some situation we want to know what is the probability of this event. Okay. Similarly, we want to know what is the probability of this event. Okay. Because the event growing up, right, become bigger and bigger. And but you know, a core of probability theory is to compute the probability of an event, right? And the event may be a little bit sophisticated. Right, you can't define the event directly, but we know sometimes we can describe event as something that we have an increasing sequence of event, and the target event would be the union, or we say the limit of these sequences. Yeah. So this is the target event, and we want to find compute its probability. Okay.
The probability of union of all the events.
Yeah, and these events are increasing sequence. Mm-hmm.
Would that not become sample space eventually? If we
Not necessarily. Not necessarily. Well, I can show you. In our example of a lifetime of light bulb, right? So suppose the events here, it's say here. Okay, so it's this event. Okay, and as n going up, so you can see this going up, right? Because when n is big, become bigger, this is also bigger, right? Okay. And what is the union? The union will be 0 and 1, but it's open, and it will approach to 1, but never reach 1.
wouldn't 1 minus 1 by n is the
So the union okay. So E1, so you can see, yeah, E1 consists of only 1 point, it's just 0, right? E1, E2, half, right? And E3, in general, En. Is that correct? So this becomes, so this EE2 is 1/2. E3, etc. So each of them become bigger and bigger, right? It's an increasing sequence of events. And then their union, when you take their union, it becomes to this half-open, half-closed, half-open interval. But never reach to 1, never. Never. Okay. Okay, so that so limit, the concept of the limit of a sequence of events applied only to situation. Always remember that. Okay, one is when we have an increasing sequence of events, or when we have a decreasing sequence of events. And the continuity of cycle continuity of probability function. Right, so if a sequence of events is either an increasing or a decreasing sequence of events in F, then the probability of the limit of En, okay, is equal to the limit of the probability of En. Okay. And we know this is the probability of U. Oh. Okay. It depends. If it's increasing, then the limit is just union. All right. And if En is decreasing, then the limit of En would be the intersection of all En. Okay. Right. Yeah.
N is greater than equal to.
Oh, equal to one side. Okay. Okay. All right, so proof. So consider an increasing sequence of events first. Okay, so now we can see E1 and E2. E3. En. Okay, so it's become bigger and bigger. Okay, and we can see this part is E2 minus E1, and this part is E3 minus E2, and this part is En plus 1 minus En. Okay. Okay, so we define F1 equal to E1 and Fn equal to En minus 1 for all n greater or equal to 2.
So
Mm-hmm.
events are not disjoint. E1, E2, they are not disjoint.
No, they become bigger and bigger. We consider an increasing sequence. So E1 is contained in E2 and contained in become bigger and bigger, right? Yes, so this become bigger and bigger. So it's E1, E2, it should become bigger and bigger. And we see that, so this part, right?
Yes.
It's not in E1, but in E2, right? So it's the differences. So we define Fn today. So that's F1, F2, etc. is a sequence of event of mutually exclusive events. Okay, and we can reconstruct so we can reconstruct it. Okay? So this is defined to be, so this is F1, this is F2, defined to be F3. This is defined to be Fm plus 1.
They are mutually exclusive.
Yeah, because the F events are mutually exclusive, right? By our construction. So they are mutually exclusive. Because before we apply XM3, we have to make sure we have a sequence of mutually exclusive events, right? Before we apply countable activity.
Before we apply what?
Countable activity. XM3 just has a name called countable activity, right? Mm-hmm.
The exam theory talks about mutually exclusive.
Yeah. Only for, and also for finite activity, also for finitely many mutually exclusive events. Okay. So before apply additivity property, you have to make sure they are mutually exclusive. Okay. So that is the reason why we actually do decomposition. Okay, just like here. So from the increasing sequence of events, En, we define a sequence of mutually exclusive events, F1, F2, etc., by this definition. Okay, and we know we can recover the original event E sub n by F sub I, right? Okay, so this become to the building blocks, even though they may not be atomic, but I mean say they are. So we can combine them together, and they are disjoint union. So I put that union there. Any questions? Okay. Okay, so now okay, one more thing. The union En, okay, becomes to be the disjoint union. Okay. Okay, now, so by countable activity, and finite activity, okay. So we have Pen equal to summation I from 1 to n probability of Fi. Okay, this we apply finite activity, and the probability of the limit n goes to infinity En, which by our definition is union. Okay, but we know this is equal to the disjoint union I from 1 to infinity Fi. Yeah. Okay, and so this is summation. Okay. So finite activity is here, and the countable activity is here. Any questions? This is from here. Okay. If you disjoint. So this one goes to here, and that one go to here. Yeah. Okay, I make errors. Okay, good. And this is we know this is a serious sum of non-negative numbers. So by the definition, it's the limit of the partial sum. Yeah? From calculus, right? Okay, good. And this is Fi is equal to Pen. Okay, so from here we reach to there, and this is the end of proof. Oh no, not yet. For the increasing sequence of events. Is that okay?
This one is for increasing sequence.
Yeah, only for increasing sequence event. Yeah, so because we consider an increasing sequence event first, right? Yeah. And now consider the decreasing sequence of events. Now, and so we know that that's the complement of En, the complement of En, right? Is an increasing sequence of events. Okay. The complement becomes increasing. You okay? Okay. So that the limit of En complement, the probability of that is equal to the limit probability of En complement. Because we just proved that.
Just make it this one, E complement?
Now it become smaller and smaller, right? So En is decreasing. So the situation here would be like why not? And so this is E2. It becomes smaller and smaller. En plus 1. So it's shrinking. And the complement, if En is decreasing, then the complement will be increasing. Okay. I compared to.
Right. Because so if E2 is decreasing, it contains every other event. So
Yeah.
leaving all that.
So this is bigger one. You may compare with E and F, right? And this is sample space. And the E complement would be the green part. And the F complement, F is bigger, right? So F complement would be so this is F complement. So you can see F complement is smaller. In here, E is smaller, but E complement becomes bigger. Yeah. Okay. Yeah. So if this En is decreasing, then the complement of En becomes increasing. Okay. And we have proved that for increasing sequences, limit of this sequence has probability equal to the limit of the probability of each term.
So now the proof is done.
Not yet? Okay. Okay. So, okay. And but the limit of n goes to infinity in complement by ours okay. By definition, because this sequence is increasing, so the limit by definition is just the union. And by De Morgan's rule, we know this is De Morgan's rule. Okay. De Morgan's law we have. Okay, it's here. This is complement. So this is implies that the probability of limit n goes to infinity is the probability that see, and this is 1 minus probability of it's okay? So this is by proposition 2.4.1, right? We know that. And 1 minus probability of limit and goes to infinity of En. Okay. Because En is decreasing, so the limit of En is just their intersections. Okay? Now, so we go back to here. So this limit, the left-hand side. Okay? So that we apply them. So 1 minus probability of limit n goes to infinity En is equal to the limit and 1 minus probability of En again, right? But this is constant, so 1 minus limit okay. Alright, so probability of limit equal to the limit. Okay, and again we have the result. Any questions?
So we took the limit in this step. Yes. How did we like the next one?
This one?
Yeah, this one. Because one is constant, so we can take the limit.
Oh, it's from here. This is limit of P of E, right? Okay. This is again by proposition. Yeah, 2.4.1. Yes. Yeah. The same reason. Yeah. Yeah. So that we apply De Morgan's law because we want to relate it, this one to the limit of En, right? But this is the limit of En complement, right? So the relationship is here. The relationship is here that the probability of this limit is actually equal to 1 minus the probability of the limit of En. Yeah. Okay, so we have that, this one. Okay, and so there is a corollary 2.6.b. Okay, it's called continuity of probability function. At the null event empty set. Right. So if we know if En is a decreasing sequence of events such that its limit is the empty set, which means that the intersection of this En is the empty set. Okay, so if this is the case, then the limit, okay, then the limit of PE, okay, which is equal to 0. So we know this is limit. Okay, and so this is P, and this is 0. Okay. So the important thing is the limit of PE is 0. So whenever, if we have, if the limit of a decreasing sequence of event is the empty state, then the probability of En, okay, because this is also decreasing, right? This is decreasing, this is decreasing, and the limit is also equal to 0. Okay, so because the probability of the empty state is 0. Okay, so we call this spare case as the continuity of probability function at the no event.
En is decreasing to 5.
Yeah, to 5. Which means that En is a decreasing sequence event, and that their intersection is the empty state. Because we here, right? The limit defined to be intersection. The notation here, right? So, which means that the limit is their intersection, because it's in decreasing sequence of events.
Because it's a subset, right? So
Yeah, because when En becomes smaller and smaller, right? Becomes smaller. And their intersection is the empty state. If we know that, then the probability of En, because the probability of En becomes smaller and smaller, right?
Right.
Yeah, and the limit also goes to 0.
We don't have to prove this, right?
Well, I already proved it. What we want is you can eliminate that. The statement is here, okay. Okay, and the proof. Maybe I write it here. Okay, so the limit of n goes to infinity PE is equal to probability of limit. Okay. So this is being proposition 2.6.1, right? From the previous proposition. Okay. And the limit, this is given, right? This is the MSA. And the MSA has 0 probability, right? I think I proved that before. It's, I think it's proposition 2.3.A or B. Let me see. A. Okay. Before. Okay. And we're done. So that's why it's called corollary, because it's a simple consequence of proposition 2.6.1. Proposition 2.6.1 is stated in the textbook. Okay, it's in the textbook. Yeah. Oh, okay. Sure. You need this. Okay, great. Okay.
Can these prepositions be used to solve any questions?
Well, that's a good point. So that is the next proposition. C. Oh, by the way, that would be A. Yeah, the first one. Because previous one is in the textbook, I'm sorry. So that would be A. And this is B here. I'm sorry. Yes. Okay. If a real valued function P on a sigma algebra F satisfies one non-negativity at P of E greater than or equal to 0 for all E in F. Second, normalization P of X to event is equal to 1. Third, finite additivity if E1, E2 up to En are mutually exclusive events in F, then the probability of their disjoint union equal to their sum of probabilities. Alright, so we have only finite additivity. And the third, fourth, continuity at the empty state if En decreasing to the empty set in F, then the limit probability of En goes to 0. So if we have these four conditions, then P is a probability function P is a probability function on F. Okay. Remember the last proposition in section 2.5, the last section, we give a method to construct or to uniquely specify a probability function on a sigma algebra on discrete sample space, right? That only for discrete sample space. But if the sample space is not discrete, right, then the last proposition in the last section cannot apply in this case. So, but in many situations, we still want to identify whether a real value function defined on a sigma algebra to be a probability function. Okay, and the axiom number 1 and axiom number 2, they are quite simple to verify. Okay, so non-negativity, normalization, they are quite simple to verify. The trouble is the countable activity, because we have to handle what? We have to handle a sequence of mutually exclusive events, and this sequence is an infinite sequence. So in many situations, it's difficult to do that. But finite activity is much more easier to prove, to show. Okay, especially if you show that for 2, only for n equal to 2, and they are mutually exclusive and satisfy the identity, then it's quite easy to extend to arbitrary n by induction. Okay, so in general, finite activity is much more easier to prove because you can do it just by induction. Okay, induction is a very common tool, right, to do that. All right, but that would be not enough. So we need one more thing. So we have to prove the continuity at the null event. So we have to prove that if we have a decreasing sequence of events, and the limit of the decreasing sequence is the empty set, then we have to show that the limit of probability of En goes to 0. Okay, so we need to show the continuity at the null event. Okay, once you check 1, 2, 3, 4, then by this proposition, you are sure this real value function is a probability function. Means that it will satisfy the countable activity property. Okay, so this proposition is going to ease our job of justification, whether a set function to be a probability function. Okay, and so this applies to uncountable sample space. Well, sample space is which is not discrete.
And
yeah.
Discrete sample space is we can count the.
We count. Because if it's countable, then we can apply the last proposition in previous section, right? The proposition 2.5.e.
Which was for discrete?
Yeah, for discrete.
So discrete means that we can count.
Yeah, we can count. We can count the samples. But this is for general case.
General.
Yeah, this is for general case, especially for sample space which is uncountable. For example, when the sample space is an infinite interval or any just an interval. Okay.
For example, in the case
of lifetime, yes, the lifetime case, yes. All right, so the only thing we need to check is surface to show that P is countably additive. Okay, this is the only thing. By using finite activity and the continuity at infinity. Okay, so we have to show the quantum activity. So let Fn, Fi, I greater than equal 1, be a sequence of mutually exclusive events in F. Okay, and we let E sub n, okay, to be the disjoint union of for I from n plus 1 up to infinity of Fi. Okay. Okay. So Fn is just the disjoint union of the F sub I, except the first n events. Okay. So I is from n plus 1, etc. Okay. It's good. Okay, so then we have the disjoint union of F sub I is equal to the disjoint union of I from 1 to n of Fi and the disjoint union of En. Okay. Or you can say I from n plus 1. Okay, but by our definition, we know this is Fi En. Okay? And the intersection of En the intercept. We know En so En is, you can see it's a decreasing sequence of events. Okay? And their intersection, okay, is equal to the empty set. Why? We have to show why this is true. All right? Otherwise, omega contains in so that it contains in okay, maybe I will exercise for you to show it why the intersection is the empty set. Okay. So that the En will go down to the empty set. Okay. Okay, so this is all our preparation. Okay, so now by finite additivity, so now we will show that the union okay. Okay. So this joint union here is the probability of Fi. Okay. So we have n plus 1 events, okay, union together, and this is a summation f sub I plus V of En. And so this is by finite additivity. P. Oh. Okay, but this is the value too. Okay. Right, and this is for all n greater than equal to 1. Okay, and by taking n goes to infinity, so we have, because this is always true, right? So probability of this joint union, I from 1 to infinity, f sub I, okay, is the limit, n goes to infinity of summation okay, plus P of En. Okay, and the limit P of Fi plus the limit P of En. Okay, and this is equal to the series sum of P of Ei plus 0. Why is 0? Because that the En has limit empty set. So by the continuity at the empty set, this limit is equal to 0. Okay, so by continuity at phi. Okay, so we proved that. So this is the countable activity here. Okay, so we show that for a sequence of mutually exclusive event f sub I, the probability of their union is equal to the summation of the probability of f sub I for y. That is the countable activity. Okay. Okay. So we prove this proposition. Okay. Okay, and so I will give an online lecture on the coming Saturday, the March 2nd. Okay. Okay, and you can watch the
You mean tomorrow?
no, the Saturday. Tomorrow is Friday. Yes. Yeah. Okay.
And that lecture will be from this chapter or the next chapter?
Next chapter, because I finished section.